encryptions that will be based on this signature is I will send over the receiver B will send over to A first his identity and the R part of the signature. And now look at this verification equation. The G to the S part can be recomputed from R and B and from the public key of the certification authority. And let's call the G to the S key, K. And now there are encryption schemes that for which for which encryption key has the form G to the S, where S is the decryptor key. This is El-Gamal encryption. Okay, it is based exactly on this math. So therefore, once we compute the public key using the R part of the signature and the signed message, we can encrypt under the key derived from this. And how does the encryption work? Okay, this is El-Gamal encryption. If K is my public key, I encrypt by taking the base G of known base of the group to a random number and taking the key to the random number, hashing the key, and XORing with message. Anyway, this is maybe slightly technical. The idea is that I will try to convince you in 3 sentences that being able to decrypt such encryptions is equivalent to breaking a hard problem. Okay, so being able to decrypt, so while for Schnorr signatures, outputting the whole signature on unsigned message, there is a known proof that reduces that to breaking discrete log. Similarly here, we know that our scheme is secure because we are able to reduce the ability to decrypt. Ouch. Sorry, I pressed the wrong thing. So we know that our scheme is secure because we are able to show that ability to decrypt on an unsigned identity using any R chosen by this malicious receiver. Such ability also reduces to computing some problems that is believed to be hard, namely computational Diffie-Hellman. So this is how we do it. If you look at this encryption scheme, these two values, they are distributed just like, so K to the U is equal G to the U to the S, because K is equal G to the S. So therefore, these two values look like this. Some random value Z, and M XORed with Z to the S. Okay, a hash of Z to the S. Therefore, if hash function is random, the only way to output M is to query the hash function on Z to the S. Okay, so decrypting is equivalent to, on some random Z, actually computing Z to the S, so that to be able to query this hash function. Okay, so we know that a successful decryptor must compute Z to the S for a random Z. Okay, and now in a similar technique, just like proof of a Schnorr signature shows that from 2 successful executions, you can so if I see 2 challenges, C and C2, which are the result of this hash function, and 2 parts of the signature, I can recompute the discrete log. That's why passing the Schnorr, so forging the Schnorr signature is equivalent to computing the discrete log. Similarly, this thing, if I pass it in 2 different instances of the execution, I can recompute from it the Z to the X value, where X is the discrete log under the certification authority's key. Okay, and this is exactly the Diffie-Hellman problem. So, seeing G, Y, and random Z, I'm able to compute Z to the X, where Y is G to the X. Okay, so okay, this goes a little quick. So basically, this is for just a sketch for if this was not clear, I apologize, but it's hard to sketch these security arguments and have them fully detailed at the same time. Okay, so that's it for the secret handshakes that are linkable. Yeah, and the protocol involves there's basically two exponentiations for the sender and one exponentiation for the receiver. There is one more exponentiation to verify the possession of the proof of possession that is inside of the decrypted message. So basically, we have two exponentiations on both sides, and 2 rounds really, because well, it's really 3 rounds because Alice has to somehow be informed that Bob passed it. So the only really way to do it is Alice also embeds a nonce in all this encryption, and Bob sends back the nonce. So it's 3 rounds. But 3 rounds is minimal for explicit authentication anyway. So this looks like a pretty minimal protocol, even though it has this extremely paranoid privacy properties. Okay, but this is an even more paranoid one, okay, where you also want to avoid the linkability. So I hide my policy, I hide all my tickets from anybody but the person that matches me, and moreover, I'm unlinkable. Okay, so no 2 occurrences of me can be put together. So okay, so where was the linkability of this protocol? Well, simply that these pseudonyms are exchanged, okay, and that the trapdoors, and that is just an artifact because we treat the trapdoors as the signatures on the pseudonyms. So it's chicken and egg, whatever. The 2 things together. If I wanted to increase this number of pseudonyms, so for example, give Alice 1,000 one-time pseudonyms, I could do that. Give her 1,000 random numbers, but for each of them, I would need to give her a signature. That's a cost. Moreover, like in practice, I don't believe something like this could really work. So when Alice is lost, okay, and I need to revoke her, suddenly the revocation list, normal revocation list should be proportional to the number of people in your organization, right? I mean, much less so, right? Because you don't revoke most of the people in your organization usually, right? So revocation list should be small. Suddenly now I need to revoke all these one-time things that I give all these one-time pseudonyms. Also, in practice, I think that somebody could attack you, like just keep engaging you in a conversation, pretending to be your friend, right? So you will just use up all these one-time certificates because you don't know whether this is still an attack or this is actually a person that, in the middle of the attack actually does want to talk to you, right? So you will exhaust these one-time certificates in this way if you try to, if you really try to use them one time each. Okay, so we want to avoid somehow these pseudonyms, okay, and actually the solution is quite simple too. So what we do is we replace the encryption, affiliation-hiding, signature-based encryption with affiliation-hiding, signature-based broad